Okay, so last time we looked at energy eigenstates. This time we're going to give a special symbol for those. We're going to give those phi. So phi sounds a lot like psi, so it's a special version of a psi. That when you apply the Schrodinger equation, you end up with the same function back. So even though there's all sorts of complicated stuff going on over here with a second derivative with respect to x and a potential energy that could be anything, you end up back with the same phi. You end up back with the same state multiplied by the energy eigenvalue. Now we're going to be dealing with several different kinds of energy eigenvalues, so we're going to give those a label n here. N's just going to run starting from 1, 2, 3, etc. For some problems it'll run from 1 up to infinity, for some it'll run from 0 to infinity, and for some problems n will run from negative infinity to infinity. The important thing is it's just a label, right? So you start and stop it whenever you need to for the problem. As an example last time, we looked at when you have zero potential energy, so when you have a flat landscape, you end up with a complex exponential for your eigenstate with an energy eigenvalue of p squared over 2m. Pretty straightforward to get, and basically, in principle, for any v, you can end up with these energy eigenstates, although as we saw in the first couple episodes, it's not always possible to do that exactly, so we have to resort to numerical techniques. But what I want to show you today are how these phi n's can become building blocks for building other functions. A lot like Lego bricks, right? You can build anything you want out of Lego bricks. You just have to start with these nice little discrete things. You add a bunch of them enough together, you can end up with any kind of shape that you want. Let me show you what I mean by this. So what we want to be able to do is take psi of x and t, right? Our wave function, the thing that goes into psi. And we want to be able to take a summation over all these n values, whatever n is running over. We have some coefficients, so C just stands for coefficient. We'll have our energy eigenstate here, and this piece is just a function of x. I might not have made that explicit over here, but this energy eigenstate is just a function of x. And then we're going to multiply by e to the negative I ENT over h bar, just like we had last time. Now the reason this is useful to us is because this separates x and t, right? Because this psi, this can be any kind of function. This can be any kind of wild function as long as it satisfies the Schrodinger equation. But this setup allows us to take the x dependence on one side and the t dependence on one side and worry about them separately, which makes the problem easier to deal with. In particular, this makes that initial state easier to deal with, right? Because at the beginning of every quantum mechanics problem, you've got to specify what the initial state is. And the reason I like to do this is because t equals 0 in this complex exponential, that's easy. That just makes that 1. It's e to the 0. It's 1. So we'll have sum on n, cn, phi n. So this set of energy eigenstates and the set of coefficients is a set of instructions for how to build the initial wave function psi. So you can take the cn's and use that to build your psi. Right? So you can take a set of cn's, use that to build your psi. Maybe you have a list, maybe you have a formula for the cn's, maybe you have some experimental data or something for what the cn's are. You can use that to build your psi, but you can also go the other way. You can also take psi at x and 0 and use that to deconstruct the cn's. Let me show you how this works. So this deconstruction process works by something known as Fourier's trick, where if you know what the initial shape of the wave function is, you can get out what these cn's are. Once you have the cn's, you get the psi x of t right away from these cn's right here. So let me show you how we get this. So we'll start off with this little piece here with psi of x and 0 equals summation on n, cn, phi n of x. And we're going to add a couple of things onto this equation here. The first thing we're going to do is we're going to pick a different psi. So let's pick a different value for an index. We're going to multiply by phi m. Right? The letter m is different from the letter n, So these two are not the same. Well, at some point it'll be the same, right? Because we're summing over all the n's. So for most of the terms over here, n and m will be different. But for one magic term, they're going to be equal. The magic term is going to be important later. The next thing we're going to do, because we love to do this, we're going to integrate both sides over x. And you sit there saying, why do you want to integrate this? Well, for one, because we love integration. But for a second reason, because these phi's always carry a special property. The integral of phi n with phi m dx, and I actually need to make this a complex conjugate, just since we do have complex exponentials over there. This thing is always going to equal 0 if m doesn't equal n. Right? So if m does not equal n, you can always set up your phi's so that they cancel out in the integral, right? And you've seen this happen with some functions, right? You've seen that if you integrate x times x squared dx, and you go, say, from -1 to 1, you see that you get 0. Even though these two functions are not expressly 0, because you've got an odd function times an even function across symmetric bounds, that's going to come out to be 0. Well, that's how the phi's are. The phi's always are. You can see that in the example over here. So let's get rid of this piece here. Let me show you how this works out with this example. So let's suppose you've got integral e to the I p1 x over h bar e to the negative I p2x over h bar dx. Let's suppose your p1 is not equal to p2. Right? They've got different indices. They're different values. That means you've got to take this e to the I p1 minus p2 x over h bar dx. And let's suppose you're taking this thing, you've always got to have some range you're going over. Let's suppose you're going from x equals, let's say, negative 2 pi to 2 pi, right? It could be anything as long as it's symmetric, as long as it's whatever range you want to look at. The thing is, right, this complex exponential, e to the I something, is always cosine of the thing up here plus I sine of the thing up here. Anytime you go over symmetric bounds like this, this integral goes to 0 and this integral goes to 0. The only way it doesn't work, if you have p1 equal to p2, then you've got e to the I p1 minus p1 x over h bar, and that whole thing is just equal to 1. So the only way you can save this from going to 0 is if p1 equals p2. It's a really cool property. It's kind of like vectors, right? Because if you have an x hat and a y hat and you take their dot product, you get 0. If you take x hat and x hat and take their dot product, you get 1. You get either 0 or 1. So that's why we call these things orthogonal. Right? Just like those vectors are orthogonal to each other, they're at a right angle, these functions are orthogonal to each other. They're not at a right angle. That's kind of hard to imagine, functions being at an angle. But they are orthogonal in the sense that you only get non-zero if they're the same, and you get 0 if they're different. So we have that work out here, where these two are 0 if they're different, but equal to 1 if they're the same, or they might be equal to 1 times some coefficient, like a 2 factorial or a square root of pi or something like that. There's some constants in there. But they're equal to 1 or some number if m does equal n. Here's the cool part. So you've got integral phi star m, psi of x and 0 dx going to equal. Now we got to start thinking about this summation, because we've got two conditions, right? We've got if m doesn't equal n, then you get 0. If m does equal n, then you get 1. Here's the thing. You're running over every possible value of n. So let's suppose your m was 10, right? Let's just pick one, right? It doesn't really matter because you're going to be summing over all of them anyway. So this m is 10. So you start out with c of 1. 1 and 10, those are different. That'll give you 0. 2 and 10, those are different. So it doesn't matter. It gives you 0. 3 and 10, doesn't matter. They're different. Going to give you 0. You're going to keep getting 0 until you get to n equals 10. As soon as n equals n, it picks out that term and it says that term is special. I get to keep that term. All the other terms are going to go away. So this integral kills off every term except where m equals n. So over here, you'll end up with, let's see, you'll end up with an integral. You'll have a cm, excuse me, right? Because this thing just comes on for the ride. You'll have an integral of phi m star phi m dx. That thing is usually equal to 1. It might have some other coefficients or something to it depending on the function you're working with, but let's just say it's equal to 1. The important thing is it's equal to a constant, not 0. So what that means is your cm, each coefficient is just integral phi m star psi x and 0. So if you know the psi at the beginning, if you know your wave function at time t equals 0, you just do this integral for every phi m that you're interested in. You can get out that coefficient. Boom, you've got those coefficients. They can go into the summation that I erased a minute ago. You can turn this into psi of x at any t now, right? So you start with just t equals 0. Now you've got psi at any t going to equal sum on m cm phi m of x e to the negative I e n t over h bar. So what we want to do, we want to be able to take this integral. Now integrals are not an easy thing to do, right? Derivatives are wonderful. I can take the derivative of anything, but integrals, I can only do a handful of integrals and only on a good day. But this is what computers are for. So what we're going to do in today's code, we're going to learn how to do this little deconstruction here, get out these coefficients using a numerical integration code.
All right, so to use Fourier's trick, first we need to define the wave function that we are trying to get the coefficients for. So this function has a real part and an imaginary part. Let's start out with a simple sine function here. Then we need to provide the basis set that we're interested in. So down here, I'm going to use the sine and cosine set. We'll get to the Hermite polynomials in a little bit. But for right now, we'll try out the sines and cosines. And here's where we do the down here is where we do the integration. So we're going to carry out Fourier's trick for all the n's that we want. We're going to start with an n min, work our way up to an n max. You can set this to be whatever values you need for the problem you're working on. And so we need to figure out these coefficients. Now these coefficients can be complex. So we have a real part and an imaginary part. And then here is where we'll figure out the real part. So we take the basis function, that's the sine and cosine that we set earlier, and we multiply that by the real part of the function that we want the coefficients for. And then same thing over here, basis imaginary part, function imaginary part. Then to get the imaginary part of the coefficient, we need to take the crisscross of these. So I need to take the real part of the basis function times the imaginary part of the function you want, and then the imaginary part of the basis function times the real part of the function that you want. And notice I end up with just one minus sign here. Just because of the way those i's end up squaring, I end up with a negative sign down here. This is an integral, so we're just going to be adding those up as tiny little pieces, multiplied by dx, and then that will give us the CR and the CI that we want. So we're going to print this out as a table, so we'll get for each value an n, a CRn, a CR, and a CIn. Okay, so here's where we set the function that we want to get the coefficients for. So let's start out with something simple. Y equals x for the real part and y equals 0 for the imaginary part. So we just want to have x. So the result we get over here, this is the result of all of our coefficients put together. The red part's our real part, the blue part's our imaginary part. We get pretty good for the x, we get okay for the blue. That should be a 0. We'll see how we can make that better in a moment. But what we need to do is define our basis set, right? So these are the energy eigenstates that we are interested in. So we'll start out with cosine and sine. So for the real part, we'll have a cosine. And for the imaginary part, we'll have a sine. Sine and cosine always need some kind of wavelength or a range that they're defined over. So we're going to take that as x max minus x min. So that's our 10 minus negative 10. So that's a 20, which is why these waves are a little bit broad coming up on this thing. We'll skip over that part. We'll come back to that in a minute. Let's see. So what we need to do is we need to establish how many coefficients we want. Currently, I'm only going from 1 to 10, which is why this result is so rough looking. If I add more of those, let's say n equals 1 to n equals 100, I end up with a much better result, right? So my real part looks much closer to a line. My imaginary part is still oscillating around 0. We'll see if we can fix that. But basically, we need to get these coefficients, right? We need the real part of each coefficient and the imaginary part of each coefficient. Because what we're doing with those coefficients to get this graph over here is we're taking the real part of each coefficient times the basis function, the imaginary part times the basis function, and then same thing down here to get the imaginary part. And so it's graphing for me this function here, f real and f imaginary, based on this summation, based on this Fourier series. And the way we get those coefficients is with Fourier's trick. So up here is where we carry out the integral for Fourier's trick. We're going to loop over all of the n's that we're interested in because we need, we need a lot of those to get a pretty good line here. And so since these are integrals, we're going to start them off at 0. You always start an integral with 0. And then we're just going to add to those the little piece that's contributed by each step. So we take the basis function times the function you want, basis function times the function you want. Same thing for the imaginary. We just go crisscross with the terms. And then we end up multiplying those by dx. Since this is an integral, we need the width of each of those little Riemann sum rectangles to be a dx. And then I put this in here just to get rid of some of the messiness, that if the coefficient is less than some tolerance value, we're just going to set them to 0 because it must be some kind of round off error or something like that. And then we record the coefficients in this list, and here we end up with our line that is looking pretty good. So if I wanted to then take this and create a line in my Schrodinger equation wave function animator code, I can use these coefficients, all 100 of them. Boy, wouldn't that be fun to enter in? You can import them as a list or as a data file or something like that. But yeah, you can do this with any function that you want. So like, let's suppose I wanted this to be x squared. Now my red should end up looking like an x squared. There we go. You notice it has to taper off at the ends here just because the Fourier series gets messier near the end, so my red is kind of tapering off there. But I've got a pretty good y equals x squared. But let's suppose we want to do something a little more wave function-like here. Let's suppose we wanted to have a Gaussian in the middle. I can click run on this. And there is my Gaussian there in the middle. So that's pretty useful. And of course, I get my list of indices here. You notice that they start to taper off. One of the things you should see with these coefficients is that they should start to decrease with the higher order you get until eventually they're 0. And that's why even though it's an infinite sum, you can usually get away with, say, the first 10 or 20, it looks like in this case, because they get smaller as the index gets larger and the wave function gets, or the basis function gets more complicated. Now, the sine and cosine are not the only basis function you can use. We can also use the stationary states of the harmonic oscillator, which is these Hermite polynomials. So those basis functions are Hermite polynomials times e to the negative x squared over 2. The reason you need this is because Hermite polynomials, they are polynomials. They will continue on to positive or negative infinity as you go off. But this little exponential here, this Gaussian, makes them die off as you go to plus or minus infinity. The way we get these Hermite polynomials, this HP, is using a recursion relation. So you come down here and you have the Hermite polynomials. And basically, if n equals 0, then you're at the 0th Hermite polynomial, that's equal to 1. If you're at n equals 1, that's the first Hermite polynomial, that's 2 times x. And everything else is defined in terms of a recursion relation. So if you're at HP1, it's 2 times x times HP n minus 1. If your HP2 is 2 times n minus 1 times HP n minus 2. So you always go back 1 and back 2, and then your Hermite polynomial value is just HP1 minus HP2. It's this wonderful little recursion relationship, so you don't actually have to know what the polynomials are. So as our first example, we're going to try out e to the negative x squared over 2. Now that is the first, or the 0th, of these basis functions, right? Because if you put in 0 for your Hermite polynomial, you just get 1. The 0th Hermite polynomial is 1. So this is the 0th Hermite polynomial. I want you to watch what happens with this. We're going to click on run. You notice I get out the shape that I wanted. I get out this Gaussian, but look at the coefficients. They're all 0 except for the 0th one, right? Because the Hermite polynomials, once you have them weighted by this Gaussian factor, they are orthogonal to each other. So as soon as you run this function against all of these functions, you will always get 0 except when you have the 0th one. Same thing if we make this the first Hermite polynomial. Let's make this x times this Gaussian function. Notice that I get all zeros except for the first term. Let's try again with the second Hermite polynomial. X squared, what was that? 2 times x squared minus 1 times this Gaussian term. Now we're going to get rid of everything except for the second term. You notice it's picking these out. It's using that orthogonality property. I can also do this if I've got a sum of two of these. So now I've got the second basis function and the 0th basis function. Right? I get something a little bit more interesting in the graph here. And notice I get the 0th term, the second term, none of the others. Let's change that into the first basis function. Click on run here. Well, that's looking very interesting. A little lopsided wave function. We haven't seen that too much. Notice I get term 1, term 2, everything else goes away. And so it's successfully able to decompose this function into the basis functions that you're interested in using.